Hello and welcome to today's lesson on sources of radiation, which is part of the atomic structure topic in GCSE Separate Science Physics. So in today's lesson we're going to look at the different sources of radiation in the universe. So if we're successful and we learn in today's lesson, we should be able to look at the different sources of radiation, define what the background radiation is, and state the harmfulness of the background radiation. Now this is part of the AQA Separate Science Specification 4.4.3.1 background radiation, which is separate science only content. Now, the picture you can see on the screen is a Geiger-Müller tube or counter. Now, this is a device which measures the presence of ionizing radiation, alpha, beta or gamma. Every time it encounters a radioactive particle, it registers this with a sound. Now, this measurement is called the radioactive count. So the count is the number of radioactive particles which the detector can measure. This then links into something called the count rate, which is the number of radioactive particles which the detector can measure every second. So the count rate is the count divided by the time. Now, it's also important to note that we can have a measurement of what we call radioactive activity, which is measured in becquerels, and the activity is the number of radioactive decays which occur every second. Now, one decay per second would equal 1 becquerel, and at GCSE we assume that one radioactive particle or emission is produced in one radioactive decay. So we can use either activity or count rate to measure radioactive decay. Now remember, a radioactive or nuclear decay increases the stability of a nucleus. So a nuclear or radioactive decay turns an unstable nucleus into a more stable nucleus. Now the activity is the number of nuclear decays per second, and it's measured in becquerels. Now it's important to note that a nuclear decay can produce either alpha, beta or gamma radiation. Now this radiation can be measured by a detector, normally a Geiger-Müller counter, and the count rate is the number of particles recorded per second by a detector. So the unit of count rate is seconds to the -1 or per second. Now it's important to note that the count rate is not the same value as the activity in an investigation, since not all of the radiation will hit the detector after it's been emitted from the nucleus, because the radiation will be emitted in all directions but will only place the detector in one place. Secondly, the count rate is not the same value as the activity in an investigation, since some radiation, most likely gamma, will pass through the detector without being registered. So if we look at our Geiger-Müller counter, which was actually invented by a scientist called Hans Geiger, who was Rutherford's assistant for Rutherford's scattering experiment, we can actually record the amount of radioactive emissions. Now this is important to note, as you'll always record a small amount of radioactive emissions in any place you place a Geiger-Müller counter. Now this is actually called the background radiation, and we can find this radiation everywhere in the world, because anywhere a Geiger counter is placed in the world, you'll measure a count. So there's ionizing radiation around us all of the time. So background radiation can be found everywhere on Earth. So radiation is detected everywhere we know on Earth. Now the level of background radiation and its radiation dose can be affected by two factors: the occupation you have and the location in which you are in. So where you live affects the amount of background radiation you're exposed to. The job you have affects the amount of background radiation you're exposed to. Now, jobs which have the highest exposure to background radiation include hospital workers, aviation workers, and power station workers. Now, just to clarify, there is no place on Earth which has no radiation. The level of radiation we find generally around us is called the background radiation. But it's also important to note that the background radiation is extremely low and therefore unlikely to cause cancer and mutations in humans, so it is not going to cause any illnesses. Now the background radiation comes from two main sources: natural sources and man-made sources. So we need to consider these two types of background radiation. Now natural background radiation tends to come from radon gas in the ground, buildings and the ground. You've got cosmic rays and food and drink, whilst man-made background radiation tends to come from nuclear power stations, nuclear weapons tests and medical uses. So just to clarify, radiation naturally comes from radioactive substances including the ground, around the air, the building materials and the food that we eat, especially food with potassium in it. Now, radiation is also found in cosmic rays from space, and some rocks contain radioactive substances that produce a radioactive gas called radon. So this leads to different values of background radiation being recorded in the UK. Now you'll notice in this diagram that there's a higher background radiation reading recorded in Cornwall and Devon, as they're composed of radioactive rocks which can produce radon gas. Now in addition, this rock is granite, as granite contains trace amounts of uranium in its structure. Now the higher values are still not large enough to cause a greater risk to inhabitants, but it's just interesting to note that there's a slight variation in the background radiation across the United Kingdom. So just to summarise, the natural background radiation can come from cosmic rays, rocks, soil, plants and animals, but you can also get human background radiation or man-made background radiation. Now human activity has added to background radiation by creating and using artificial sources of radiation. Now these include radioactive waste from nuclear power stations, radioactive fallout from nuclear weapons testing and medical procedures. Now artificial sources account for about 15% of the overall average background radiation dose, and nearly all of the artificial or human background radiation comes from medical procedures such as radiotherapy or receiving x-rays for x-ray radiographs. In fact, you're more likely to receive a higher dose of background radiation working in a hospital compared to that of a nuclear power station. So to summarise, we have man-made or artificial or human background radiation in the form of nuclear missiles, nuclear power and medical uses. Now it's important that when you carry out an investigation with radioactive materials, you've got to consider the background radiation. Well, how can you do this? Well, to get an accurate value for the radioactive emissions of a certain radioactive material, you must first measure the background radiation of the room and then subtract this from the readings from the material. So for example, if the background reading is 50 millisieverts and the reading from the material is 80 sieverts, that tells us the actual reading of the radioactive emission from the material is 30 millisieverts, 80 minus 50, because 50 of the 80 are coming from the room, so the other 30 must be coming from the material. Now just to note, the sievert is another unit of radioactivity. It's a measure of how dangerous the radioactivity is to humans, which varies on the type of human tissue irradiated and the type of radiation which is doing the irradiating. Now it's typical to note that a dose of 1 sievert gives a human a 5% chance of developing a cancerous tumour. Now your sievert dose depends on the dose and the type of radiation you're exposed to. So for example, exposure to alpha particles for a long time leads to a high dose of sieverts, but exposure to gamma rays for a short time leads to a low dose of sieverts. So in an investigation you must consider and subtract the background reading of your radiation. So the Geiger counter must record the count before the radioactive source is placed in the room. This will give us the background radiation count. Now just note, the Geiger counter must record the count before the radioactive source is placed in the room, because the background radiation cannot be measured after the source has been in the room, as trace amounts of the source, little tiny particles, may have been left behind and then affect the actual value of the background. Now the most reliable results are taken for the longest time possible and are repeated many times. This is important because radioactive decay is a random event. So this means you can't get anomalous results for radioactive decays. You can't make a mistake when recording these particular values. The results cannot be anomalous, they can only be unlikely, because it's based on random chance. Now the radiation count is then measured with the radioactive source in the room. The true radiation count is therefore the measured count with the background radiation count subtracted, which we call the corrected count. So for example, we could measure the count to be 200, but we then measure the background count to be 50, so therefore the actual value, the corrected count from the source, is 150 becquerels. If you do not correct your count, you'll have a consistent error in your results from the background radiation. Now it's important to note that an error which is a consistent error in a scientific investigation is called a systematic error. Now the most common type of systematic error is a zero error, but this is another example of where you would get a systematic error. So, what do we know? Background radiation is around us all of the time. It comes from natural sources such as rocks and cosmic rays from space. It comes from man-made sources such as fallout from nuclear weapons testing and nuclear accidents. And the level of background radiation and radiation dose may be affected by occupation and or location. Now, the dose of background radiation is measured in sieverts. Now, a normal exposure to the background radiation is harmless. However, if this increases due to work in hospitals or on aeroplanes or due to a disaster, this can cause harm. Now, when carrying out an investigation, the background radiation must always be subtracted from the measured values. So let's summarize what we've learned in today's lesson. Some atomic nuclei are unstable, and the nucleus gives out radiation as it changes to become more stable. This is a random process which we call radioactive decay, and the activity is the rate at which a source of unstable nuclei decays, and is measured in becquerels. The count rate is the number of decays recorded each second by a detector, such as a Geiger-Muller tube. Now, a background radiation is around us all of the time, and it comes from natural sources such as rocks and cosmic rays from space, but also man-made sources such as the fallout from nuclear weapons testing and nuclear accidents. And the level of our background radiation and radiation dose may be affected by the occupation you have and the location in which you are at. So if you've been successful and learned in today's lesson, you can look at the different sources of radiation, define what the background radiation is, and state the harmfulness of the background radiation. So I hope you've enjoyed today's lesson on the sources of radiation in the atomic structure topic of GCSE Separate Science Physics. Thank you very much for listening to today's lesson, and have a lovely day.